So now we are going to discuss metal halides. Alkali metals as well as alkaline earth metals form metal halides in the following way. So they can react with hydrohalic acids, giving you hydrogen and metal halide, or for alkaline metal hydride we can say this way, MX2. Okay, so that we have already discussed. Similarly, metal oxides of alkali and alkaline earth metals react with hydrogen halides, giving you MX metal halides. So plus H2O we have. Same way we have metal hydroxides can also react with halo acids, okay, and we are getting metal halides this way. Or metals can react directly with the halogens also. So that reaction also we have done already. So that we are getting metal halides. Now, if I am talking about alkali metals and alkaline earth metals, if we consider their ionic characters, that goes on increasing. Lithium chloride and beryllium chloride are typically covalent in nature, but the beryllium chloride is more covalent than that of the lithium chloride. So ionic characters increases down the group. And it is because of Fazan's rule. This is due to Fazan's rule. So we know that in a Fazan's rule, if the size of the cation is very small, there will be greater polarizability of electrons, so that the electrons are lying at the center of the two nuclei. That gives the characteristics of covalent bond. So lithium chloride, even if it forms an ionic compound, it has a certain covalent character. But in case of beryllium chloride, it is purely covalent. So I can say this way, lithium chloride LiCl is less ionic than NaCl, than KCl, than rubidium chloride, than cesium chloride. So this is almost have a covalent characters, less ionic character. But in case of beryllium chloride, BeCl2 is actually covalent. While rest of the alkaline earth metal halides are ionic in nature. Okay. So structure of BeCl2. So this is the structure of BeCl2. Again, because of the vacant orbitals, there will be formation of network structure. So the chlorine atom is actually bridge between two beryllium atoms. So this is that structure, and it is because of covalent bond. It is the one chlorine is actually sp hybrid, beryllium is sp hybridized, the sp hybridized orbital of beryllium is overlapped by p orbital of chlorine. Okay. Since beryllium has vacant p orbital, that is also occupied by donation of electron from chlorine. But in case of alkali metal halide, this is not the case. Okay. Here we need to follow the Fazan's rule. Now, solubility of metal halide. In both the cases, it goes on increasing as we move down the group. Increases as moving down the group. In both the cases. Okay. Beryllium chloride is and lithium chloride, or rather beryllium chloride is less soluble in aqueous, but it is easily soluble in organic solvents. So here we are talking about solubility of metal halide in water. Okay. Melting point. So LiCl has a lower melting point than NaCl. But further the melting point goes on decreasing. Because of the decrease in lattice energy. Here this has an ionic bond, this has a covalent characters. So because of the ionic bond, there is a perfect pattern of crystal structure, and because of that NaCl ionic crystal. So here it has a highest lattice energy, and therefore the melting point is very high. In case of alkaline earth metal, because of covalent compound network structure, beryllium chloride has greater melting point, and that melting point goes on decreasing as moving down the group. So BeCl2, then MgCl2, then CaCl2, SrCl2, then BaCl2. So simple order. This is all about the halides of alkali and alkaline earth metal.